Today I want to go over a few theorems from graph theory. The first theorem I want to look at is it says that the sum of the degrees of all the vertices is equal to twice the number of edges. Now I'm going to claim that probably is common sense, and the reason is every edge has to be incident with a vertex. In fact, every edge has to start at a vertex and end at a vertex. And if it starts and ends at a vertex, then it really adds 2, the number 2, to the total number of degrees in the graph. So that's a little insight as to why it's true. And now here are just a couple of examples. Here's one graph. Okay, this vertex is of degree 2, that one 2, that one 2, that one 2. So if I sum up all the degrees, what do I get? I get 8. You will notice that I have how many edges? 1, 2, 3, 4. So I have 4 edges, and the sum of the total number of degrees is 8. It matches my formula. The sum of the total number of degrees always has to be twice the number of edges. By the way, that also means that the sum of the total number of degrees has to be even. Has to be an even number because what? It's twice the number of edges. Okay, here's another example we can look at. This vertex is of degree 2. This is 3, this is 3, this is 2, and this is 0. And if you sum up the degrees of all the vertices, I claim you get the number 10. Well, if you count the edges, lo and behold, 1, 2, 3, 4, 5. Therefore, again, and this will always be the case, that the sum of all the degrees is twice the number of edges. You see, 10 is 2 times 5. Okay, the next theorem we have has to deal with an Euler cycle. When do you have an Euler cycle? And the answer is, according to this theorem, that you have an Euler cycle if and only if, number one, it has to be connected. That means you have to be able to walk from any vertex to any other vertex. And finally, every vertex has to be of even degree. So if I have one vertex of odd degree, then this theorem tells me I do not have an Euler cycle. All right, again, I claim this theorem is common sense. It just depends on how common your sense is. How can you think about it? Well, first off, if you have an Euler cycle, that's a cycle, remember, that connects every vertex and every degree and every edge. So it's a cycle that goes through every edge and every vertex. Okay, well, if that's the case, then the graph has to be connected because I have to be able to walk through all the edges and all the vertices in one cycle. Okay, now why must each vertex be of even degree? Because if I have an Euler cycle that connects all the vertices, then every time I go into a vertex, I also have to go out of a vertex. Now, I can go into a vertex more than once, but every time I walk into a vertex, I have to walk out of a vertex. And if it's a cycle, then I'm not allowed to walk over the same edge twice. So what that means is that the degree of every vertex has to be 2 because every time I walk in, I have to walk out on another edge. All right, so this theorem gives us a way to where we can just look at any graph and determine whether or not it's got an Euler cycle. To have an Euler cycle, it's got to be connected, and every vertex has to be of even degree. All right, so if I look at this one, notice every vertex is of even degree. They're all degree 2. But this graph is not connected. Why? Because I cannot walk from this vertex to that vertex. Notice, just to review a little bit, this graph has two components. Here's one component, here's the other one. All right, so what can I tell you? This graph does not have an Euler cycle. Why? Because it's not connected. Okay, now let's look at this example. This graph is connected. I can walk from any vertex to any other vertex, but look here. I have a vertex of degree 3. And my theorem says to have an Euler cycle, every vertex has to have even degree. So if I have one vertex of odd degree, like in this case, one of degree 3, I can tell you that what? This does not have an Euler cycle. Finally, I might as well look at an example that does have an Euler cycle. Check this graph out right here. First off, it's connected. I can walk from any vertex to any other vertex. Secondly, this vertex is of degree 2, 2, 2, and remember this vertex is of degree 4, but the point is every vertex is of even degree, and therefore I claim it's got an Euler cycle. Now, if you would like to see the Euler cycle, let's start here. I go from here to here to here to here to here and back. I have covered every vertex and